All right, so far we have volumes and lengths with calculus. Now we're going to move on to area. So to motivate this, I want you to consider a graph of y equals mx. M will be positive just for the purposes of this discussion. Let me go ahead and draw a rough sketch of what this looks like. So we would have the x-axis. Okay, so we have the line y equals mx. Now I intend to rotate that about the x-axis. So it's going to be rotated about the x-axis. And when you do that, the shape you're going to get, as we've done this 100 times, I don't know how about 100 times, but many times before, you're going to get a cone shape. Let me see if I can make that better. And what I want to do is apply this to a problem that we're going to do. So I'm going to develop some formulas. And what I'm going to do is I want to try to determine an area. Say I have x1 and this ends at x2. So I'll do this. If I concentrate on just that one region there, okay, what does it look like when it's revolved around? Well, if I look at just this region here and then revolve it around, I'm going to get something like this. What's called a frustum of a cone. So there's x1 right there. And right in here is x2. So find the area of the frustum. Frustum is just the piece like I've shown here, a chopped off cone. Well, one thing you ought to know is in general, when you do have a cone, there's a couple of things that we need to know. One of them is the radius, and the other is what they call the slant height. Surface area of that cone pi RL. So I'm going to apply that to this problem to figure out a formula for the surface area of that. Now keep in mind, when I talk about the surface area, I'm talking about just the area of the outside here. We're not including the base. And keep in mind also, this is supposed to be a hollow cone. So all it is boundary material. All right, so let's look at our situation then. If I want my frustum there's my frustum. That is going to equal So let's say I come in here, and here's x1, and then here's x2. So anyways, if I take this cone and I subtract from it the smaller portion, so if I go and take this full-size cone and get rid of this small piece, then I will get the area of this. So what's the area of this guy right here? Well, it's going to be pi. The radius now will be that radius. So let me go ahead and draw that. That length, if you remember, the equation for this line up here was mx. So that is mx2. And then this length up here, hopefully you can see that we have a right triangle where the base is x2, the height is mx2, so this length is x2 squared plus m squared x squared using Pythagorean theorem. I'm going to pull out an x2. Everything's positive here, so I don't have to worry about absolute values. And so that piece there is pi mx2 squared times the square root of 1 plus m squared. Similarly, down here, I have pi times, and here, like before, I have mx1 is the radius, and this length, as before, is x1 squared plus m squared x1 squared. So I'll have times x1 times the square root of 1 plus m squared. So that's pi mx1 squared times the square root of 1 plus m squared. Alright, so I have this quantity minus this quantity. And that gives me pi. What I'm going to do is factor out the things that are common. I have pi, an m, and a square root of 1 plus m squared. Times x2 squared minus x1 squared. So that gives me the formula, or a formula, for the area of a frustum. So whatever x2 and x1 is, I can throw them in here. Now, let's apply this to a real-life situation. As an example, consider the line y equals 1/3 x, and x is between 0 and 3. Compute the surface area of the solid generated by revolving a line about the x-axis. So our situation looks like the following. So we're revolving that around the x-axis. The surface area of this cone is a equals pi RL. Well, what's the radius in this case? Well, when you plug in x equal 3, the height is 1. So the radius, the base radius, is 3. So I get that equals pi times, the base radius is 1. And then L, well, the height is 1. And the base is 3. So I've got a right triangle 1 by 3. So that means L is going to equal the square root of 3 squared plus 1 squared, which equals the square root of 10. So that's pi radical 10. That's what we're going to aim for. So now, use calculus to derive. That answer. So with that in mind, I'm going to regraph. And we'll end it at 3 as before. And also as before, what I'm going to do is consider down here x sub 0. This equals x sub n. And then you'd have like x1, x2, dot, dot, dot. You'd get to x sub k plus 1, dot, dot, dot. And these, instead of right triangles, what I'm going to do is simply draw little trapezoids instead. Of course, this will have its own trapezoid as well. And we'll consider this region here and get a handle on that, then add them all up. So, if you look at just this piece, what does it look like when it's rotated? It'll be a frustum, as before. And of course, this part here is where xk is, and this part here is where x sub k plus 1 is. Now, we know the area of this. I'm going to call it A sub FR, or frustum. I don't want to write the whole thing out. So that's going to equal pi. And then what else do we have here? We have not that formula, but this one up here, this guy right here, m times 1 plus m squared, the square root of that. So we have m square root of 1 plus m squared, and then we have x sub k plus 1 squared minus x sub k squared. So I'm going to do a little simplifying on this. M, if you remember, was equal to 1/3. So I'll plug that in there. Let me leave the other stuff there for now. And I'll simplify that stuff a little bit. I'm going to get times 1/3 times the square root of 10 over 9. Of course, the square root of 9 is 3, so we're going to end up with pi times the square root of 10 over 9 times xk plus 1 squared minus xk squared. Now, suppose n goes to infinity. Then the trapezoids have widths that are going to 0. Thus, I want you to think about something now. If this is super thin then x sub k is approximately x sub k plus 1. They're approximately equal to each other. And then the area of the frustum is going to be approximately pi radical 10 over 9. Now what I'm going to do is factor the difference of squares. So actually this is equal. Let me take that out. But now it's approximately equal to pi radical 10 over 9 x sub k plus x sub k. Now one of the things we always use for this piece back here is delta x, because we use the same width for all of the subintervals. So I get 2 pi radical 10 over 9 x sub k delta x. Now add up all the areas. Of the frustums. So we get sum k equals 1 to n 2 pi radical 10 over 9 x sub k delta x. I almost went to the integral. So this is going to give us the area that we're looking for. Of course, by now I hope you realize that this can be written as an integral. The beginning was 0, the end was 3. I have 2 pi radical 10 over 9 x dx. The 2 pi radical 10 over 9 is simple to get rid of. I'll just pull it out front. 2 pi radical 10 over 9. The integral of x is x squared over 2. And that'll go from 0 to 3. Plugging in 0 is no big deal, but 3, I'll plug that in. So I get 2 pi radical 10 over 9 times 9 halves. The 9's cancel, the 2's cancel, and we are left with pi times radical 10, which is the area we tried to get. For my first example, and you'll see that these are all pretty simple to set up. Let's see, compute the surface area of the solid that is formed by rotating the curve y equals x cubed. X is between 0 and 1, about the x-axis. Now, if you go back, let me come back for a minute here. And I want to go to this version here. Let me have this frustum again. Now, I'm going to do a couple of things to it. This, remember, it was approximately equal to pi m 1 plus m squared, and then I had a delta x. And then when we took it to the integral, it looked like this. Well, I want to remind you of some things. Here, if you'll remember, the original function up here, this was the original function. So I'm going to rewrite this. So the original function was mx. The derivative of mx is just m, so write this m as the derivative. Now, I could have done all that stuff with the general function and derived this formula, but I thought it might be best to do it with the line. So anyways, all this is an aside. Keep that in mind. This guy right here is the formula we're going to use. So the solution to the problem at hand, since we are going from 0 to 1, the function is x cubed. The derivative of the function is 3x squared. And we end up with 2 pi, the integral from 0 to 1, x cubed times the square root of 1 plus 9x to the 4th dx. I should probably make that 4 look more 4-ish. And you can do this. If you allow u to equal 1 plus 9x to the 4th, you'll be able to do this problem. Your final answer should be exactly pi over 27 times 10 to the 3 halves minus 1. For the next example, compute the area of the surface generated when the curve f of x equals the square root of 5x minus x squared, where x is between 1 and 4, is revolved about the x-axis. So the area, once again, is 2 pi. The integral starts at 1 and ends at 4. The function itself is 5x minus x squared. And then we take 1 plus f prime of x squared. The derivative of this, since there's a square root on the outside, the first thing we get is 1 over 2 times the square root of 5x minus x squared. Now, using the chain rule, I've got to take the derivative of what was inside, which is 5 minus 2x. Now that quantity there is all squared. Somewhere I've got to get a dx in here. Let me do a little simplifying. Let's see, I'm going to get 5 minus 2x. That quantity will be squared. The denominator is easy enough. I'll get 4 times 5x minus x squared. Now the trick for an integral like this is to actually take this quantity here and multiply it through. So when I take this square root and I multiply it through, this piece right here will become 5x minus x squared. Then when it comes and distributes to the second piece, it'll cancel out the denominator, and I'll end up with 5 minus 2x, the quantity squared, all over 4. In the end, you'll end up with exactly 15 pi.